Hello and welcome to another walkthrough video of a past paper, and today I'm going to do OCR Physics Higher Tier 1 Paper 1 GCSE, and the code for this paper is 8463. Okay, so question number 1. Figure shows a wind turbine. Wind turbine may generate electricity when the electricity is not needed. Two methods that can be used to store the energy from the turbine are method A, heating water to a high temperature, and pumping water uphill into a reservoir. So in this question, you have given two methods to store the energy. One is the way in which you are heating up the water by 80 degrees, and one is that you are pumping the water to a 500-meter height. And in the table, you can see that the heat energy that is stored in the water is about 33,600, and the wasted energy is 40%. And the pumping water uphill to a height of 500-meter is actually consuming 490 kilojoules per 100 kg of water, and 25% of it is lost, and it can be stored up to some mountains. Okay, so they have asked us to compare the two methods of the energy storage and give advantage and disadvantage, and they're asking us to do some kind of calculations as well. So I'm going to do some calculations for you right now. I am writing it down and then I'll be back. So in the method A, I'm going to write for you. In method A, you can see that the total energy was um, 33,600. So you're first of all writing the efficiency formula, and you are going to find out the wasted amount of energy, the total one that is given to you, into 100. So the lost energy for method A is 40%. The wasted amount of heat you have to calculate. Okay, the total is about 33,600 into 100, and from here the wasted amount of energy that is going to get is so again in method A, we are going to do some calculations for the wasted energy and the stored energy per 100 kg of water. So you can see in method A that the water has been heated up to 80 degrees centigrade, and the total energy is 33,600. This is the lost percentage. So if I want to calculate the lost or wasted energy, then what I need to do, I need to apply the percentage efficiency formula. Okay, and that is actually equals to wasted divided by total into 100. Why? Because the efficiency formula is actually output over input, or you can say the given divided by the total. Okay, the given and the total is 33,600, right? So you can say that the wasted one we don't know, we need to calculate that. The total one is about 33,600, so you are just writing it 33,600 into 100. All right, the percentage of the lost amount of the heat is 40. This 100 is going the other way, so let me write that completely. Okay, so from here the 100 is coming to the left hand side, and the 33,600 is going to the left hand side as well. And from here you are going to get the wasted amount of energy, and that is 13,440 kilojoules per 100 kg of water, as it is mentioned in the table. Okay, so if this is your wasted energy, then what should be the useful energy? So the useful energy will be, or useful, or you can say the stored energy that you have stored in the water. Stored energy will be equals to total minus wasted, right? So the total amount of energy was 33,600, right? And the wasted is 13,440. So in total, it is 20,160 kilojoules is the useful energy that you have stored. So what is the drawback or the advantage of this method A? So we can say that in method A, let me change the color for the pen. In method A, the problem is we need insulation, otherwise the heat energy will be lost to the surroundings, right? So we can say that we need insulation. Insulation needed. And the second one is appropriate spaces needed. Appropriate space is needed, right? And even though the percentage is low, you can see that even though the percentage is low, but the amount of energy that is stored in the water is much more than the method B, because in method B you only have the total amount of energy is 490, but in the method A you have huge amount of energy. So the advantage is more heat energy is stored in water, okay, then method B. Okay, so that is your advantage, and these two are your disadvantages. Okay, so that was for the method A. And what about method B? So the same thing that we have to do for the method B as well. I'm sorry, I'm running out of space. So for method B, you are going to do the same thing. And in the advantage and disadvantage, first of all, you have to say that because you are pumping the water uphill to some place, so that means you need some appropriate location, right? Appropriate location and space is needed, right? And space is needed to store, right? And the problem is that can be your disadvantage, right? And one more disadvantage is less storage of energy as compared with method A, although the percentage is high as compared with method A. And in this, no insulation is required, because in heat energy you need some insulation, otherwise you will lose the energy storage. But here you don't need any insulation, right? No insulation needed, so that can be your advantage, right? Now they have mentioned that you need to do some calculations, so let me do the calculation the same way as we have done for the method A. So the calculations will be similar to the one that we have done already. Percentage efficiency will be equals to the wasted divided by total into 100. Efficiency that is given to you for method B is 25%, that is lost, and 490 is your total. So 25% will be here, 25 wasted is something that you need to calculate. Your total is 490 into 100, and from here the wasted energy is going to be equals to 122 kilojoules per 100 kg of water. Okay, and your useful energy is going to be useful energy equals total minus wasted once again, and your total is 490 minus 122, so the answer is going to be 367.5 kg. So that was 1.3. 1.4, decreasing the amount of carbon dioxide released by different activities will help slow down climate change. Transport and generating electricity are the two activities that released the largest amounts of carbon dioxide in the UK in 2018. Explain one change that could reduce the amount of carbon dioxide released by each activity. So you should know that when the fossil fuels like petrol, diesel, kerosene oil are burned, carbon dioxide is produced. So one way is for sure to use electric vehicles. And when you use the electric vehicles, you won't burn any fossil fuel, so there will be no generation of the carbon dioxide. Okay, so you should use electric vehicles, and you should use public transport. Use public transport as it will burn less burning of fossil fuels. Okay, and due to which less CO2 generation. And what about the electricity? If we do not burn coal to generate the electricity, because in coal power plants we burn coal to get heat, and that heat is used to run the turbines, and the turbines when run they generate electricity. So in order to generate the electricity, rather we burn coal, we should use renewable energy sources like solar and wind. Use renewable energy sources, e.g. wind, solar, and when you do that, no burning of fossil fuels of coal, so no CO2. Okay. Question number 2, the process of nuclear fission is used in nuclear power stations. Figure 2 shows the process of nuclear fission. Okay, so complete the sentence by using the appropriate word from the given words. In nuclear power stations, energy is released from uranium nuclei. Okay, because we have so many atoms and so many nucleus, and when you have so many nucleus, it is called nuclei, because nucleus is single and nuclei is plural. You need to remember this. It is single and nuclei is plural. Okay, so um, the uranium in figure 2 splits into two parts and releases three neutrons for sure, because it is a fission reaction. Remember, in a fission reaction, when uranium breaks, it always generates three neutrons. Okay, and the process of nuclear fission releases electromagnetic radiation in the form of gamma rays. So the heat that is generated because of the fission reaction inside nuclear power plants, because here in question 1.4 you can also write down one method to generate electricity. Use NPP, nuclear power plants. Okay, nuclear power plants to generate electricity, to generate electricity. And when you use the nuclear power plants to generate the electricity, you actually burn uranium. And when you burn uranium 235 by having its reaction with neutron, you actually get two small elements or atoms, and you get three neutrons, and you get heat energy. Okay, and that heat energy is actually in the form of gamma rays. That is actually the total reaction. So here this n is actually neutron, and this is 235, and that is neutron, 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 and these two are the small ones. One of them is krypton and one of them is barium. This is just for your information, you don't need to remember that. Okay, so write down the equation which links energy, power, and time. So you need to remember power is always equals to work over time, and work is actually a form of energy. So you can write power equals energy over time, and from here you can say energy equals power into time. So E equals P into T. That is the relationship between energy, power, and time. A nuclear power station has a power output of 500 megawatt. So mega means 10 raised to the power 6 watts. Okay, and calculate the energy output in 3600 seconds. So you have time, you had power, you need to calculate the energy in joules. So first of all, you need to write energy equals power into time. Then power is 500 megawatt and time is 3600 second. So because of mega, you will put it like this into 3600 seconds, and when you multiply them all, you are going to get 1.8 into 10 raised to the power 12 watt second. Okay, this watt second, you are left with watt and you are left with second, so watt into second. And in the formula you can see on the right hand side, if you see, this is watt and this is second. So when watt is multiplied with second, you actually get joules. Okay, remember that. So you are going to write the answer as joules. Radioactive waste produced by nuclear power station. is simply 0.92. Okay, so 92% of 365. So 92 per means slash and cent means 100. So 92% of 365. So when you multiply that, circuit used. The student plotted a graph of resistance against the length of the wire. Describe a method the student could have used to collect the data needed to plot the graph. Okay, first of all, in this reaction, please understand what that what that experiment is all about. So here you have an ammeter. If you can take a look, let me change the color of the pen. If you take a look, this is voltmeter and this is ammeter, and you should know that an ammeter is used to measure current. Okay, and this voltmeter is used to measure the voltage. Okay, measure voltage, and you can see that all of them are connected in series, and that is the piece of wire that you are the length you are measuring it with meter rule. Piece of wire, and you are actually moving these clips left and right. So when the clips are coming close to each other, the length of the wire that is connected with the circuit becomes short, and when the clips are moving away, the length of the wire becomes long, right? So actually we need to know that when the length increases, how does it changes the resistance of the wire. So first of all, from Ohm's law, you should know that the resistance is actually equals to this, and from here resistance is actually equals to V over I. So that means in order to find out the resistance, we need voltage and we need current. Okay, so first of all, your point number one should be point number two, sorry. Measure the length between two crocodile clips, okay, using the meter rule. Okay, and after that you can do then switch the on the circuit. Okay, switch on the circuit, you can say next. Okay, and next what you need to do, measure the reading of voltmeter and ammeter. Voltmeter and ammeter, get resistance R by doing V over I, because you will get the uh, measurement in step 4. Okay, then change the length and do the same. You need to take multiple readings, for each length and take the mean and take the mean. Okay, so for example here you have the you have 40 centimeter, and here the reading is for example 220 volts or millivolts, whatever, and okay, millivolts, and here you can say 2 milliamperes. So you need to take it for this 40 centimeter up to 3 readings and take the mean. For example, one time you have 2.1, here maybe you have 20.2, and third time you may have 19.9, and for the third time you may have 1.99. So you just need to take the divide V and I each time to get the three values for the resistances R1, R2, R3. And when you get the three readings for three voltage readings V1, V2, V3, and three readings for the current I1, I2, and I3. So you need to get the mean R1, R2, and R3 divided by 3. And what is the purpose for doing this? Because when you do this, your error in measurements is always reduced. So remember that sometimes they ask, why do we take the um, mean value? So you need to say that the error is decreased in this way, okay? And take the mean. And finally, this is the most important step, because we have to find out the relationship between voltage and current, right? And then we need to plot the graph between the voltage and the current, right? So finally we are going to plot the graph, and we will say that when you have certain when you have 5 to 6 readings, plot the graph between resistance and length. That will be on y-axis because it is dependent on length. When length is increased between the two crocodile clips, the resistance is also increased. So anything that is dependent is always plotted on the y-axis, and anything that is independent, for example here length is independent of resistance, because it is up to us that we use small amount of length or large amount of length. So therefore length should be on the x-axis. Okay, length should be on the x-axis, and we will get the straight line. Okay, so is there anything else that we have to be careful with? So one precaution that you have to take in this experiment, uh, you can say that keep the current value within limit so that heat loss is minimum, sorry, so that we may not produce heat energy. Okay, and second thing is, if you get any value that looks strange, for example you got four values, one is 1.1, one is 1.2, one is 1.3, and the other one, the last one is 2.5. So that 2.5 is something like strange value, and it is quite sure that you have done something wrong, therefore you got 2.4. So we call such values as anomaly. So you should be looking for anomalies and remove them, okay, from your measurements. Remove anomalies. Okay, 3.2, figure which graph shows the relationship between the resistance of the wire at constant temperature and its length. So I just told you that the resistance is directly proportional to length, As you increase their length, resistance also increases. So for that, you can only get this graph, because when two things are directly proportional to each other, we always have a straight line graph. The student used a cell that had a potential difference of 1.5. Explain why the cell was not an electric hazard to the students in the investigation. Because this 1.5 is very small amount of voltage, and it cannot generate any electric shock. Okay, so we can say that uh, 1.5 volt is too low, and it cannot create any electric shock. So 4. Figure 4 shows a static electricity generator. The rubber belt is turned by a motor, so you can see this is the rubber belt. All right. As the rubber belt moves, charge is transferred from the rubber belt to the metal dome. Okay, here the charge is going either positive or negative, whatever. Okay, as they mentioned for the negative, so let's talk about negative. So here the negative charge is going. Okay, so figure 5 shows a student touching the metal dome of the static electricity generator. The dome is negatively charged. Explain why the student here stands up in that way. Because the students here were already negatively charged, and this was also negatively charged because it is mentioned here. Okay, so when this charge is going here, they repel each other this way, and this way repulsion, you can say repulsion, and because of that repulsion, the students here become in that way. So you can say that electrons are transferred to the here, to the hair of student, from dome to student here. Here are negatively charged also, and due to repulsion between the here negative and the coming negative charges that are coming from the dome, due to repulsion, uh, student here become like that, like shown in picture. Okay, so 4.2, the metal dome creates an electric field. What is an electric field? So it is like a home, or a boundary around a charge. For example, if somebody or some strange people come into your home, you will feel that there is something wrong with that. Similarly, when you have a positive charge and you bring another positive charge into or near to it, they always do the repulsion. Why? Because you are bringing the external positive into the field of the bigger positive charge. So this repulsion only happens up to a certain field or certain area. For example, here you have a positive charge and here you have a positive charge. They will not do anything because this positive charge is out of the field of another positive charge. So that circle that I am making around a charge is actually called field. And in order to feel or in order to experience the repulsion of two like charges, you have to bring them into the field of one another. So that is the field of another positive charge, and we call that electric field. Okay, so when these two field, when you bring them close enough that their fields started to interact, you will feel repulsion and attraction. So from here, I got to know that the electric field is actually an area around the electric charge in which another charge will face an effect if it is brought into it. Okay, so let me write that down. So here I have written that it is a region around a charge in which uh, not in which. So it is a region around a charge where another charge will experience attraction and repulsion if it is brought in. If it is brought into that field. Okay, into that field or into that region. So that is called the electric field. How does the electric field strength vary as the distance from the charged metal dome increases? So it's quite obvious when positive charges are going away from each other, their attraction or repulsion is minimized or becomes less and less and less. So you can say that the the so here I have written that as you increase the distance from the metal dome, the repulsion actually decreases, and when the repulsion decreases, it means that the electric field strength also decreases. Okay, so here a figure 6 shows the negatively charged metal dome and an earth conductor. When the earth conductor is moved towards the metal dome, there is a spark between the dome and the earth conductor. The spark transfers zero point 0.6 joules of energy and 2 microcoulomb of charge from the dome to the earth conductor. Calculate the potential difference between the metal dome and the earth conductor. Use physics equations sheet. Okay, so first of all, you should know from the formula sheet that the potential difference, which is V, is actually equals to energy over charge. Okay, so the energy that is given here is zero point 0.6 joules. So you will just write joules, and charge is given in microcoulomb. So micro means this sign is actually used for micro, and mega was 10 raised to the power 6, and this micro means 10 raised to the power minus 6. So you have to write the charge, which is 2 microcoulombs, so 2 into 10 raised to the power minus 6. And from here, the potential difference is 3 into 10 raised to the power 5 volts. And this is what exactly you needed to find. 4.5. Which of the following changes would increase the distance a spark can jump between the dome and the earth conductor? So you can say that if the resistance between air resistance, you can say, is decreased between the two domes, the spark can jump more and more, right? So you can say that decreases the air resistance because when there is no air between the two domes, there will be no external force there, no external object there to reduce the interference between the two electric fields. One is the smaller dome and one is the bigger dome. So you can see that if there is no air right here, so when there will be no air, its field and its field, they will be interacting very much easily, and therefore this spark will be able to jump at a longer distance. Therefore, you have to decrease the air resistance if you want the spark to jump more at a distance, which is more. Okay. Figure 7 shows a student putting a coin into a vending machine that sells food. The vending machine is connected to the main means electric supply. What is the frequency and the potential difference of means electric supply in the UK? So remember that the electricity that is coming into your home is actually being operated at 50 hertz and 230 to 240 volts. And that is not just for the UK, it is actually a standard worldwide. Okay, that the home electricity is always is always operated at 230 volts and 50 hertz. The vending machine identifies the value of a coin by measuring the resistance of the coin. Okay, so the coin is actually made of some metal, and when the coin is inserted, a voltage of 230 and current is flown through the coin, and when the voltage and current is flown through the coin, a resistance is actually calculated by the machine itself, and there is a specific value of the resistance because there is specific metal inside the coin, so there will be a specific value of the resistance for the coin as well. So now if you put something else other than the coin, the resistance will be different, and when the resistance is different, it means the vending machine will detect that it is not actually a coin, it is some foreign object, right? So they are saying you the power dissipated by the coin is 340 milliwatts, and the current is this. Use physics equations to calculate the resistance of the coin. So first of all, what you need to do, you need to use power equals product of voltage and current. Remember that, okay? But I know that by Ohm's law, we have uh, V to be equals to IR, right? So here we will get I square into R. Now, why did I do that? Because I only have the power and I only have the current. I need to find out the resistance. So from here, I need to do this cross multiplication and I will get the resistance. Now what is power? Power is 340 milliwatts. So milli means 10 raised to the power minus 3. 10 raised to the power minus 3 divided by current, which is 0.75 amperes. So you need to do the square. And from here, the resistance is going to be 0.60. Coins that are dirty are not recognized by the vending machine. So just one reason, because when the coins are dirty, it means there is an insulation on the metal coin. So when there is some insulation, it means less current will be flown. So when less current is flown, resistance will be different. Resistance will be calculated different. So less current flows through the coin. Uh, Different value of current will be measured. Okay, so you can say that R will become different. Okay, due to changed value of current, because R is equals to V or I, and therefore due to that reason the vending machine will not, due to this vending machine will not uh, recognize the coin, will not recognize the coin. Okay, figure it shows part of a different circuit that is used to monitor the temperature inside the vending machine. Okay, the circuit symbol for the thermistor has not been included. Draw the circuit symbol for the thermistor. So the circuit symbol for the thermistor is this. You just make a block box and this. Okay, figure 9 shows how the resistance of the thermistor varies with temperature. So you can see that when the temperature is going high, the resistance is coming down. So it means there is an inverse relation between resistance and temperature for thermistor. You can easily see that, okay? So the cooling system inside the vending machine turns on turns on when the temperature of the thermistor is above 20 degrees centigrade. Determine the potential difference across the thermistor when the temperature is 20 degrees centigrade. Use physics equations. Okay, so first of all, what is the temperature at 20 degrees Celsius? So here's you have, so I believe this is 80 degrees centigrade, right? So first of all, you need to connect a thermistor here, and when you connect the thermistor here, okay, its resistance is 80 ohms, and you can see that 480 80 ohms are connected in series. So first of all, you need to calculate the total resistance of the circuit, and since they are connected in series, so you have to add them straight away, and the total resistance is 480 ohms, and the voltage that you have here is 12 volts. Okay, so now you need to find out the potential difference across the thermistor. So first of all, what I am going to write, I'm going to write down the formula for V equals I into R, and R is actually the total resistance, and I'm using it to find out the current. Use it to find current first of all, okay, because in series the current remains same. So voltage was 12, I is unknown, and the resistance was 480. So from here you have to calculate the current as 0.025 amperes. Okay, now you should know that the circuit is actually a series circuit, and in series you should know that the current remains same. So the same current I equals 0.025 ampere is actually flowing through the thermistor. Okay, so we know that the resistance for the thermistor is 80 ohms, and we know that the current for the thermistor is also 0.025 amperes. So the potential difference for the thermistor should be V equals IR. Okay, and I we already have 0.025 and 80, and same current will be flowing through this fixed resistor as well, because in series current does not change. So when we do that, we are going to get 2 volts. So that is actually our answer. Okay, let me complete that up here for thermistor. V equals I into R. I is 0.025 into R, which is 80, and when you multiply that, you got 2 volts. Question number 6. In a ride at a theme park, a person is strapped into a pod that is attached uh, to 2 stretched bungee cords. So these are your bungee cords. Which energy store increases as the bungee cords are stretched? Of course, elastic potential energy, because you are stretching them up. Okay, elastic potential energy. So when the pod is released, the pod accelerates upwards. Before the pod is released, the extension of each of the 2 bungee cord was 8 meters. So that means this each pod is actually stretched by 8 meters. Okay, The spring constant of each bungee cord is 735 Newton per meter, because we know that when something is stretchable, we always have the formula applicable to that is F equals kx, where this is called spring constant. Okay. And the spring constant in this case is actually 735, and this formula is applied always to springs or anything that is elastic, which can be stretched or compressed. So here the rope is actually extendable, so we can consider that rope as a spring. The mass of the pod is 240 kg. Gravitational field strength is 9.8 Newton per kg. Calculate the maximum height reached by the pod. So when the stretched cords are released, the pod will go up, and they're actually asking you at how much height the pod will go up in the sky or upwards. Okay, so we need to use the equations to find out that height. First of all, we know that we have elastic potential energy. So the elastic potential energy is actually equals to elastic potential energy is, we also call this as elastic strain energy. Okay, elastic strain energy formula from the formula sheet, and it is equals to half k delta x square. Okay, and the extension that was given to us is 8 meters, so it means the extension, which is in meters, is in 8 meters, and the spring constant is 735 Newton per meter. All you need to do just to plug in the values in the above formula, it will be 735 and it will be 8 square, and the elastic potential energy is going to be 23,502 joule, and that is for one rope. Okay, since we have two ropes, one rope energy for two ropes, you need to multiply EPE with 2. Okay, 23,502, and that will be equals to 47,040 joules. Okay, now we know that the change in elastic potential energy is always equals to change in kinetic energy or change in gravitational potential energy. Okay, because the body is moving up, so its gravitational potential energy will be increasing because body is moving up, and the elastic potential energy will be decreasing because the extension is being reduced, right? So you will say that the loss of EPE, because one form of energy, which is actually elastic potential energy, is now giving itself to gravitational potential energy, and it is actually turning into gravitational potential energy. So you will say that whatever the EP is going, it is actually being converted into gravitational potential energy. So you will say that the loss of electrical potential energy, elastic potential energy, is equals to gain in gravitational potential energy, right? So this was your total, and this is your uh, gravitational potential energy, which is mgh. And now the mass for the for the person which is standing in is actually 240 kg, right? So if I put in the values, 4707 equals 240 into g value is 9.8 into h, and after cross multiplication I am going to get 47040 over 240 into 9.8, and when I calculate all of it, I used to get for 20 meters. Okay, the actual maximum height reached by the pod will be lower than the correct answer in 6.2. It means we calculated the value 20 meter, means the pod will reach the height of 20 meter, but they are saying it will not reach up to 20. It will be going up, not 20 but something less than 20. So why is it so? Because of air resistance. In our calculations we have ignored the air resistance, but in actual there will be air resistance because of air resistance. Okay, and secondly, it is not possible that all of the elastic potential energy stored in the rope is completely converted into gravitational potential energy. There will be some elastic potential energy left in the in the rope. So because of that, not all of it will be converted into GPE. So you will say some or not all of the energy is converted into not all of EPE is converted into GPE. Okay, question number 7. Figure 11 shows a measuring cylinder containing some water, which a student used to measure the volume of the metal ring. So, when measuring the volume, the student's eyes was in line with the level of the meters. For example, here it was. Which type of error would have been caused if the student's eye was not aligned? So it can be parallax error, and parallax error is actually called random error or human error. Since it is not mentioned here in human error, so we will say it is a random error. The student tied a piece of thick string to the metal ring and lowered the ring into the water. So just one reason why the student should have used thin string instead of thick string. So what actually the student is doing, the student is actually tying up a piece of thick string to the metal ring. Okay, so there is a metal ring going in to the water, and along with that you have a thick string and a thin string. So that ring is actually in the hand of student, and the string is actually going into the water. So the question is, the ring is in the hand of the student, and the thick string or thin string is going into the water. Now they're asking you whether thin string should be used or thick string should be used. So the answer is thin string should be used, because thick string will displace more water, which affects the measurement of the volume. Okay, thin string should be used. Thin. So here I have written the answer. The thin ring should be used because if thick ring is used, it will displace more water, due to which volume measurement can be disturbed, which is actually our purpose of this question, to measure the volume. Okay, just like you can see here, we are measuring actually volume. 7.3. Table 2 shows the results: volume of water in cubic centimeters and second and third. The true volume of the ring was 0.44 cubic centimeter. Even without using the string, the measuring cylinder could not give an accurate value for the volume of the ring. Give one reason why. Very important, very important question. So you can see that the volume, exact volume, is actually in two decimal places, whereas if you take a look of this beaker or cylinder, the volume is actually in one decimal place. For example, this is 1 and this is 0.8. This is 0.6, this is 0.4, and this is 0.2, right? So our answer, the minimum answer that we have is actually in one decimal place. So it means the maximum answer that we can get is 0.4 or 0.6. We cannot get 0.44 because the measuring cylinder is not giving us two decimal places answer. Okay, because so is the answer, because measuring cylinder is accurate up to one decimal place. So that means the maximum reading that can be obtained from the cylinder is 0.4 cubic centimeters, not 0.44. The student used a balance to measure the mass of the ring. After the ring was removed from the balance, the reading on the balance was 0.02 grams. How could the student use the readings from the balance to determine the correct mass of the spring? So if you have not placed anything and it is giving you 0.02, so it means it is an additional mass which has to be subtracted from the uh, measured mass. Okay, subtract 0.02, which is additional mass, or zero error, because of zero error. Subtract 0.02 from the measured mass. Okay, 7.5, the student determined the density of the ring was 21,500 kilograms per cubic meter. The volume of the string was 0.44 cubic centimeters. Calculate the mass of the ring and use the physics equation sheet. Give your answer in kg. Now, very important. First of all, the formula for the density is actually mass over volume. Okay, and the formula for the unit for the density is cubic meter per second, a kilogram per cubic meter, sorry, and the mass here is in kg. Okay, and this volume is in cubic centimeters. How do I know? Because of this. So you can see that this is mass divided by volume. Okay, so now here you can see the volume given to us in cubic centimeters. So first of all, you have to convert your volume into cubic meters. Convert volume cubic centimeters to cubic meters. Okay, so for that, all you need to do, 1 meter is equals to 10 raised to the power 2 centimeter. So 1 centimeter is quite inverse to it is this. So 1 cubic centimeter, if you take the cube on both sides, it will become uh, this much. Okay, yeah, this much. So that should be your answer. Now you need to do, the volume will be 0.44 into 10 raised to the power minus 6 cubic meters. So here you have the volume, here you have the mass, which is 21,500, sorry, density is 21,500 kilogram per cubic meters. Now you need to find out the mass. You need to do the cross multiplication. Okay, just put in the values, 21,500, and volume is 0.44 into 10 raised to the power minus 6. And when you multiply them together, your answer is going to be 9.46 into 10 raised to the power minus 3 kg. Okay, a student investigated how the pressure in a fixed mass of air varies with the volume of the air. Figure 12 shows the equipment used. It's like a pump or a syringe. Syringe is like a mini pump for your football. So when the plunger was pushed slowly into the syringe, so that is the plunger, the temperature of the air remains constant. Explain why the pressure increased. Because when you push it down, what happens? When you push it down, molecules comes close to each other. When they comes close to each other, their collision rate increases, their energy increases, therefore the pressure also increases. Okay, so you can say So I have written down the answer as when the plunger is pushed down, the particles are coming close to each other. Due to that, collision of the particles with each other and with the walls of container increases. And when they're in striking to each other or colliding with each other and the walls of the container is more and more and more, it means they're putting more force on each other and on the walls of container. So we can say that as a result of it, the pressure increases. Okay. A fire piston is a special type of syringe that can be used to start fires. Figure 13 shows a fire piston. The plunger is pushed quickly downwards and compress the air and fire this cotton wool. When the air is compressed quickly, the temperature of the air increases. How does an increase in the temperature affect the air particles inside the piston? So, of course, when temperature is rising, their kinetic energy is rising, because if somebody is giving you more heat energy, you will be jumping more and more and more, right? So, we can say that the kinetic energy is actually increases, not the potential and not the separation, because they're coming close to each other. So rather they'll be separate, they'll become close to each other, and moving energy is not potential energy, it is kinetic energy. When the air is hot enough, a small piece of cotton wool in the piston catches fire. The energy transferred to the air in the piston is 0.0130 joules. The mass of the air in the piston is 2.6 newtons per minus 18 minus 8 kg. Specific heat capacity of air is this. Calculate the temperature change of the air. Use the physics equation sheet. So you have here specific heat capacity, which is this. You have the given mass this, and you have the energy this. Okay, and the specific heat capacity formula is mc delta theta, or in some books it is also written delta t, and you need to find out delta t. Okay, you need to find out the delta t, which is change in temperature. So if you want to find that out, you just need to plug in the values. E is 0.013, m is 2.6 into 10 raised to the power minus 8, and C is 1.01. Okay, and finally 1.01 kilojoules. Oh, kilo. So for kilo you have to put 10 raised to the power plus 3. Okay, and then finally you have the change in temperature. Just take them to the left hand side and do the division. Okay, and from here our answer is going to be 495. Okay, so question number 9. A teacher investigated the radiation emitted by two different radioactive sources, A and B. Figure 14. Figure 14 shows a radiation detector positioned near one of the radioactive sources. Okay, so that is the detector and it is placed near the radioactive source. The teacher measured the count rate at different distances for each radioactive source. Figure 15 shows the results. Okay, source A and source B. Okay, explain how figure 15 shows that source A only emits alpha radiation. So this is for source A and this is for source B. And you can see that the radiation measured by B is up to this, whereas the radiation measured by A is up to this distance only. Why? Because when you are increasing the distance between this and this, alpha cannot travel to longer distances, so alpha will be stopped here. So when alpha is stopped here, stops here because of the air, you won't get any radiation or any counts in the detector, because detector will be the one which will catch the alpha and takes and plot them here. But since alpha are all blocked in the air, so no alpha is reaching to the detector, and you can see the graph is almost reaching the bottom. Okay, so that is the clue that the uh, alpha are shown by the uh, graph A. And how you need to write this? So this is the answer, because alpha has low penetration power. Therefore, they cannot travel to more distance, and hence the counts which are coming to the detector are therefore decreased to background level at 4 centimeter and onwards, because they are not exactly zero, because some radiation is always present in the background because of the space, because of the sun, because of the natural radiation coming out from the earth core, etc. Okay, it cannot be zero uh, anywhere. It cannot be zero anywhere. So 9.2, figure 15 cannot be used to determine if source B emits beta radiation or gamma radiation. So we know that. Explain how an absorbing material could be used to show which type of radiation is emitted by source B. Oh, that's a good question. So we know that the beta is easily blocked by aluminium, right? So if I put aluminium here, for example, if I put an aluminium sheet here, so if I put an aluminium sheet here, and I see that the counts are decreasing, what will that mean? It means that the radiation is actually beta, because beta can easily be blocked by the aluminium sheet. So place place an aluminium sheet between the detector and the radioactive source, and if counts are dropped, then it means that it will be the beta radiation, and if the counts are not dropped, because it will be gamma radiation, because gamma cannot be blocked by the aluminum sheet, but beta radiations can be blocked by the aluminum sheet. 9.3, suggest one safety precaution the teacher would have taken to reduce the radiation dose to the teacher received. So you need to remember the TDS, okay? Time, distance, shielding. This is the principle, time, distance, and shielding. You can write any of the one, okay? Either you may write 1, or either you may write 2, or either you may write 3. Spend less time near radioactive source. So you need to spend as less time as possible radioactive source. So the time, distance, and shielding principle says spend as less time as possible near the radioactive source. And if you don't do that, increase the distance between you and the source, and you can easily do it using tongs to handle the source. Tongs means something that holds the
source. It is like a specific type of equipment. We call it tong. Okay, it's like a big stick. And the shielding, use lead made apron. Lead is a metal which blocks all the gammas. So in hospitals and where the people use radiation, they always wear the lead coats and the lead gloves and the lead goggles to avoid their eyes, their hands, and their body from the radiation exposure. Okay, so just one safety precaution that the teacher would have taken to avoid becoming contaminated. So it's quite obvious that you should not touch the source directly because it can be stick to your hands or fingers. So you be using gloves, lead gloves, lead gloves. Okay, you should be using lead gloves or apron or anything to handle the source.